We're going to take a look at another disk method question, and we're going to be revolving it around a horizontal line again, which means, again, it should be in terms of x. Let's go ahead and read this question together. Find the volume of the solid generated by revolving the region bounded by the curve. So the first curve we have is y equals 3 minus square root of x. The line y equals 3. So this time it's not necessarily the x-axis. It's a different line, still a horizontal line, y equals 3. And the line x equals 9, so it's going to be bounded by that line. So we'll go ahead and underline that one as well. The region is going to be revolved around the line y equals 3. So again, y equals 3 is a horizontal line. We're going to follow the same steps as we did last time to solve this problem. So the first thing we want to do is make sure that the equation is in terms of x. Both equations, actually. So y equals 3 is okay, right? Because it's equal to a number, not in terms of like 3y squared or something. And then, of course, y equals 3 minus x, what we really want to look at, that is indeed in terms of x. It's 3 minus the square root of x is equal to y. And so remember, when you're revolving around a horizontal line, make sure that everything is in terms of x. So these two equations are what we're looking at. And since they both can, this one contains an x and this one's equal to 3, which is a constant, we will be good to go for step 0. I'm going to go ahead and check that off, because in both cases, y is by itself. Again, y equals 3 and y equals 3 minus square root of x. Okay. Step 2 is to draw the Cartesian plane. Step 1. Steps 1 and 2 are basically the same. We're going to draw the plane and we're going to draw our curves. So first of all, we'll just go ahead and draw y equals 3, which is one of our curves. And the other one is 3 minus square root of x. Now notice that we are, let's see if I can get the right color here. All right. Notice that our two curves have been drawn, but notice that these we are revolving around y equals 3. Our axis of revolution is the same as one of our curves, and that's important. It has to be that way in order for the disk method to work. If it's not that way, we'll resort to washer method. The other part of what we were reading says that it's also bounded by x equals 9. So this rightmost line is x equals 9. But notice it didn't give us the leftmost line, and that's because that's where they cross. So they actually cross at x equals 0. So it's going to go from x equals 0 to x equals 9. And remember, that's the real indicator of what your equation should be in terms of. If the range is in terms of x, so it goes from x equals 0 to x equals 9, then your disk method or your disk formula must be in terms of x as well. Which, like I said, it pretty much already is. This is 3 minus square root of x, and this is y equals 3. Y is by itself. This is what our disk is going to look like. So for step 3, we're just going to basically draw the shape of the disk, kind of like we did when we draw the cross sections. We can see that our very last disk is going to have a diameter of 6, right? A radius of 3. That kind of brings us to visualizing what this looks like. Again, I'm going to be using an app created by Tom Brzezinski. Thank you for making this app. This is basically our region, and what happens is when we rotate this solid around, we see that we are going to get something that looks like this. All right, and again, this is our outermost disk, or our biggest disk, which has a radius of 6 and a radius of 3 and diameter of 6. We can see the smallest disk over here is basically 0, right? And it's going to get bigger as we move out because the difference between square root of x and 3 is going to get bigger. So our radius is going to get bigger and our solid's going to get bigger. And this is kind of what it looks like if we look at it from this perspective. So we just want to find the volume of this big solid right here. That leads us to our next step. After we draw the shape of the disk, again, we won't have really access to this, especially if we're taking a test. Step 4, we want to sketch the lines of intersections of the disks and the curves on our Cartesian plane. So this is kind of the cross sections of all of our individual disks. We will be integrating all of these areas of these circles from 0 to 9. Step 5 is very important. We want to determine the radius of our disk in terms of x. We talked about this before. We're just going to go ahead and move to this particular scenario. We notice that our axis of rotation, A, y equals 3, is above our region being rotated. Okay? When it's above, we want to use our radius formula as A minus f of x. Okay, so in this case, what it's going to be is 3 minus this curve right here. Now this curve is 3 minus the square root of x, so it's going to be 3 minus the square root of x. So again, you're taking your axis of rotation and subtracting your curve. In this case, I'm putting my curve in parentheses because this minus is going to end up distributing to both of these. Now the 3's are going to cancel, and we're going to end up with our radius formula just being the square root of x. Now, and the reason we do it A minus f of x in this case is because the axis of rotation is above the area or the region that we're rotating. If it were the other way, it'd be f of x minus a, and that's what we did for example 1. Step 6, determine the limits of integration, the range of the disk cross sections, and again, that's going to be going from 0 to 9. That will be our limits for our integral. That leads us to step 7, which is to set up the integral. We're going to be going from 0 to 9 of pi r squared, but again, normally we just pull pi out of the integral since we can just multiply it at the end. So pi times the integral of 0 to 9 of our radius squared. In this case, it's going to be square root of x squared. Okay, so you know, what happens when you square the square root of x? It just becomes x, right? And so again, we kind of lucked out here. This will be easy to integrate when the square root cancels. All right, so step 8 is going to be making the integrand easy to integrate. Again, that square root of x squared will cancel and just become x dx, and then we will be integrating this from 0 to 9. One thing you could do is just say that the power of x in this case is 1, because the integral of that is just going to be 1/2 x squared. From 0 to 9, don't forget to multiply by pi at the end. So when we integrate x or take the antiderivative, we get 1/2 x squared from 0 to 9. Don't forget your pi. We're going to plug in 9, and then of course when you plug in 0, you're just going to get 0, so it won't matter. When you plug in 9, you get 81 over 2, and I almost forgot my pi, so that's 81 over 2 pi. And if we simplify 81 over 2 pi, we get around 127 cubic units being the volume of that solid that we generated, which is pretty big, right? Seems like a lot bigger than the example we did before. It would be the approximate volume of the solid generated between the curve of 3 minus x squared and 3 from 0 to 9. That's it for this example. If you have any other questions about this, let me know.